So welcome everyone for cloud computing and big data to our lecture 5, the MapReduce computing paradigm. And in the first part of the lecture, we really understood that MapReduce is essentially just 3 phases. So it's map, sort, shuffle, and so on, reduce, right? So that's an important key message because in a way we just program map, we just program reduce, and the logic, as you have seen in the word count, but the sorting, shuffling, and grouping, we basically had no idea at all. We just think about the key structure. And this is, of course, a beauty. If you're thinking about that you send around all the different, let's say, tasks to all these different compute entities, if you have to do it your own, right? If you do it yourself with all this different programming, you would have such a code which is like hundreds or 200 lines of code. For instance, an MPI in the HPC world, we have to do this. Then we do send and receive, we do collective messages with broadcast and so on. But in the end, what you basically have here, a very sweet material of parallelization, of scalability, without doing any of this. You have no idea where it runs. All what you know is you put it to the shuffling framework, it shuffles the job, it schedules the job for you, and you get the results. So this is a simplification we basically talked about in this course. And it was admittedly a bit on the computing side again. A little bit like Spark was also very early in the course so that you can use it in the assignments. But in the end, the idea is very, very similar than Spark, as you have seen from the computing perspective. Of course, Spark then basically has the point that it used lots of memory, if you remember, in its core, which makes it then faster than Hadoop today. But Hadoop has also the second part that was basically not only having a scalable programming model and tool for computing, but Hadoop had also this part of basically being very reliable when it comes to data. And that's why they basically created this Hadoop distributed file system as a very specialized file system that always assumes errors. So everything in this file system is kind of made for errors to really deal with this on the software side. Of course, on the hardware side, there's no chance to deal with it. Hardware, which is error, which is faulty, needs to be replaced. You can't use it. But on the software side, when we abstract it, when we virtualize from it, then of course we can do some things. We can, let's say, indicate that some of the hardware device is basically error prone. When I know there's very certain important data, then I better replicate it 3-4 times, right? So that I have it always accessible. In a way, you know that from your MP3s or so from former times, how today everybody uses perhaps Spotify, but in former times you want to update your MP3 collection because you don't want to lose it when your hard disk fails, right? So of course, normal backups in a way are your small scale solution, but the big scale solution is really thinking about a file system that does very similar thing with replication strategies. And of course, being scalable. Again, the motivation, again, this part of the idea here that you have from the data center perspective is really every time there's basically an error, there's a problem with the data center, and we have to work with this on the software level, then there could be different errors. Of course, if there's a power crash, that means one of the data centers would fail, perhaps at least partly. So you want to maybe do it across data centers. It's one scale up. But here we're talking maybe, for instance, in one Spark cluster on different nodes, at least to have a replication running. There could be serious bugs. There are lots of reasons why this could, let's say, not work in the hardware. It's not always overheating of CPUs, what the majority of people always think, or overheating of hardware. So basically, you have here the module reliability, just as an example, where you have the aspects of analyzing really for a data center what metrics would be there. So what are the metrics where you basically have to see where they be just judged on, right? Do you think about the credit card? You would say 99.9, I want to have availability. So essentially when you do this, you have the problem that in a way you cannot really specify this. But of course, they operate and do statistics all the time. So in a way, they have to show you when you are not convinced and want to have your money back, that actually they did their jobs. Hence, there are lots of metrics, and some of them are basically specified here. It's mean time to failure, or basically mean time to repair a certain cluster or a certain device. And then basically between the failures is then defined as just, adding this time up. And then you basically have this formula. You have always a module. It could be a cluster, could be a certain hardware device available where you can do all the statistics. It's just one example, right? How you quantify this. And then you have the service layer on top. How long is the server down? We had the example of the virtualization. Basically, the migration time between one server and another is another one where you would say they do statistics. Just for you, I think one of the most common cases in terms of, what is basically a measure for this availability within the cloud. It's a bit more a formal way of describing it. Let's come to some more, let's say, ways. How could actually be examples of those? We had already the hardware faults, lots of discussions. Basically, there could be something hitting. This is very interesting in alpha particle sometimes, or basically having faults in software that you basically have, something badly programmed in a scheduler. It could happen. The scheduler is very essential because it schedules the job of all the different nodes. And if that is an error and suddenly two users are on the same node executing or something, then there could be massively problems, or they cannot deal with the data. So these are software errors and faults where basically we really can't work with it. Hardware design could be also occasionally that someone is having wrongly configured a switch. It's possible. It's just humans that configure at the end these large data centers, which may be another good example. Then what you essentially have here with the mistakes that you could have by maintenance personnel, basically you put the hard disk in, but you don't really connect it fully. Of course, these factors, environmental faults we have seen in the university, a flooding can happen sometimes, right? So these all is possible. And to have an approach to be ready for this, at least from the now more data side, would be to have, let's say, a very specialized file system. And I don't know if you heard RAID levels already in some of the lectures. Okay, it's something which is protecting you against data loss. There are different RAID levels, meaning normal backup, or more other strategies to really basically have a very condensed representation of data, and then different ways how to restore data if one part of the data fails. So these are RAID levels where you can be judged on, that you can be paying with. So if you want to have a RAID level, which is a complete backup, it maybe costs a lot of money because you basically have your data twice, while different other RAID levels would avoid this by having less data and they compute more to get the data back. But this is something what we actually also learn more in basically in the HPC course. So here we take it on a reasonable cloud level and say there are different of these levels that you can basically look at. And also find when you go to some of the cloud services, how you can steer this. So how it works now when you think more MapReduce connected with these file systems. We said the map files should work on some form of data. So when we have a data split, you see a little bit here, data, right, comes in. Obviously, we have to split it, like the 100 documents, we split that in 5 files, and then we send it out. Of course, it depends on how many workers you have, but they would now do the word counting on all this splitted data. Now the engine will try now to locate these map files essentially there where the data is, right? It will not now doing basically transport issues of putting the data somewhere. So you can assume you have a file system where the data is already lying, which is very close to moderate compute power, where the map task will be then executed, having access to the split of the data. And then basically you have these intermediate files, which are then more or less on the local disks, right? So these would be all the different words, always 1, 1, 1, 1, the occurrences, the intermediate results. And then the engine would fire off the reduce task based on these, and would basically then try to get the reduce task also again close to this data to then have the end result. The data is always very important. And of course, the master and the user program, they have to, let's say, they are of course over it and check that all the different workers work and that they did their work. That's why we said the head nodes, right, in Spark, and the worker nodes, there's some different, kind of work divided by them, while the master is just doing the management and looking what's happening. We have the different workers here, right, which could be that working. Good. So what else? I think that's the key message of this. There are smaller parts, of course, which I could go into detail. Whenever the split of data is done, this data locality is, of course, taken into account. However, this of course means also you need the data there. And this means also that in a way you need something where we would say, if data locality plays a very big role for me, then I need it several times, this data, right? First, to think about if many people work on the same data, you need to have the capacity of the workers there. You know, basically, if the data is there and it's very, very occupied, the cluster or the worker nodes at that particular location in the cluster from that data perspective, then it's bad, right? We cannot operate on the data, but maybe we should. So in the end, what you do is you basically have this replicated several so that this assigned task again can, you know, basically always look where is really the data and maybe where's a replication of the data where we can send these tasks for. And this is what's happening if you have your normal program, you fork, and then the assigning will take place of the assign and of the reduce task. And when it's then reading the files, it does this local writes and then basically get a remote read, basically trying to get as much as you can, also data locality, of course, but it's maybe not always possible because it's local files and maybe the availability is not there and it still works. And all this kind of interesting errors that you see here, you don't see as a user, right? You don't care about this. All what you have is you have programmed a map task and reduce task. So in normal, let's say parallelization, you would implement all of this, right? In high performance computing, that's what we do, send, receive, and, you know, distributing the data and stuff like this on different workers. Here, all of these is basically abstracted away from you so that you just have to define the map and the reduce task. And it lives, of course, from the idea of the data underneath. So we basically need this distributed file system to, let's say, remove the need for moving the files, but rather sending the small map tasks always to this data. And here you see how that basically is realized in this cluster. You have this kind of distributed file system that does now this shredding, basically of this different file parts and replication, right? So you see that chunk one of the files, right, is basically distributed across different data nodes. So now as map task, I can be scheduled when I want to work on this number one on all of these different tasks. Very simple to understand, I guess. Of course, it costs more. And now you can imagine if you want to have lots of replications, it costs more storage. And with this, the credit card, you have to swipe again for more storage costs. On the other hand, it enables you to really quickly work because the tasks are basically always very close to the computing. And of course, also when you think about you have a whole team working on it, let's say sentiment analysis on the Twitter tweets, you have maybe 3 marketing guys doing nothing else and analyzing this. How is the situation right now with our products? Then it would be also much better to have a couple of replications so that they can work in parallel also quick so that the cluster is not occupied. The interesting thing is also, of course, here you see you want to basically access one of the replicas for working, but it's actually down, right? So I cannot work today, I have to go home as a sentiment analyzer. So what you do, you have, of course, another replica you can work on. And now again, the beauty is as a user, you don't see any of that. But you just go into front of your laptop, you do maybe basically simple analysis with sentiments and so on, and then have essentially the same operation as it was yesterday. Although one of the servers went down, one of the data nodes went down with my data, I still have the data somewhere else. I can work on it. And the framework does everything for you there. It basically knows with the basically metadata where are which chunks of all the different datas. Hence, it is also a single point of failure. We come to this. There's, of course, a problem. Thinking about that the head node will die means something that your worker nodes, don't know how anymore to operate. That's one of the disadvantages of this frameworks. That's why you will sometimes find 2 head nodes deployed, right? Or name nodes, how they call them also, so that you have 2 masters in case of the primary master went down, that the secondary master can take over the management of all the workers. Because if they fail both, then the job is really gone, basically. And more notably, also the knowledge, where's all the data, right? Which is essential. So essentially a very simple strategy, but also this file system is implemented and you can use, and you just beautifully say, instead of 2 replicas, I want to have 3. And then you went a day or 3, and it will actually organize the replicas for you in that way. And it's basically also, again, very nice, usable. It has just this problem with the master and head. That is, of course, a single point of failure. But everything else is, from the usability perspective, of course, very beautiful. You don't have any interconnections to program, not message exchanges, and not even an email, right? You just send map reduce task, and they are usually prepackaged for you in a jar or so, and then you basically can use it very quickly. And again, what you see underneath, again, the same ideas we had in Spark and in the cloud, it's scalable. Now I can add 4 more nodes, or like you have seen in the video, 8 nodes, 10 nodes, 12 nodes, basically, depending on how much data you really have here, the gigabytes, terabytes, petabytes, you would, of course, think about shrinking or making the cluster broader and to have basically more data nodes and also more computing alongside. Right, I call it here data nodes so that you could realize a bit more also that the data plays a big role in this file system approach. Right, yeah, the other aspect which is interesting, and I already talked about the head node now, that this is the master that knows essentially with the name node all the different sharding parts. So you take a big file, you chunk it into different pieces, and then distribute it over basically all your data nodes. It's a key paradigm, and we already talked about that. This is, of course, slightly a problem, but if you have 2 of them, it's unlikely that basically both of them fail at the same time. And once a head node is down, or one of them, of course, they work very incredibly fast to get reinstantiated. So an interesting basically idea that was basically at that time very different from parallel file systems that we use in HPC, for instance, where we binary write in files and binary read from files from one large file, not chunking around and so on, like this framework is doing. And essentially, just to see how this replication look like, you have a certain file space, which in the real file system doesn't mean anything. You will see that when you do your practicals, your assignment, that you only work with parts of files. But of course, the parts of files have then essentially things inside, like the words we want to analyze and count, for an example, and then basically see that this is largely distributed. But the funny thing is you don't really see that. You just quickly see that maybe in a log file that you use different parts of the file. In the end, you have the result given through your reduce task. But the reality that you don't see as a user is essentially this underneath, right? That you have different data nodes with all of these different parts. What you essentially see a little bit is this in every now and then, that you have your data you want to look at, and it looks like part 0, part 1, with this different replicas. And the name node that is essentially having this information is therefore very, very important, because the tasks need to know which of the map tasks they will get. And the framework identifies this, of course, by having this name node or this metadata node, this master really working on this. While this be then the workers that just do the job, they have no idea of all of this, right? They get assigned a map task. I have this for my 1 and 2. You picked 1. Okay, we work on this with a map task, done, and send it back. So this is essentially the abstraction layer from this file block architecture, which is, of course, very often used. And again, one key user here is basically how you can connect this now for very different ideas. You see here again that HBase is basically using this as a very bottom line. HBase is a system which is, let's say, more or less working on data, but the underlying layer is just HDF files. And HBase is one of this ecosystem from MapReduce, ecosystem from Hadoop technologies that you can put on top, right? So basically, you can operate a complete idea of NoSQL value stores on top of this principle of replication. So normally we would also have then maybe in another course where NoSQL stores, if you work with this, key value stores and so on, very popular in databases right now. So this is how you do your data basically. And of course, it's already beautifully in a way stored, like you can use then in different regions and different elements on these tables with MapReduce and basically reuse this strategy. But that's how you basically scale up, and that's how you automatically be fault tolerant, while you actually use quite nicely these kind of table-like structures in HBase, and they benefit from all what's underneath from the HDFS, right, indirectly. So if a task on a specific table will fail, then it will be looked at where this table is actually replicated in HDFS, and then we'll resend the analysis task to this particular one without you knowing, right? I mean, basically, you maybe get a small notification saying, well, that's a problem, but please essentially it will be saying, I have resubmitted the job here and there where the data is. And this is something what you see Facebook is using, but all the different cloud vendors are using for their products. And that's how you can really scale, right? If you see about 1 trillion total posts, you know, most of all, basically Facebook, how quick you have to process this. So that is, of course, something which is very important. Right, so the benefits are manifold in replication strategies. So this is something, of course, which is very obvious. I don't want to lose my data, right? But of course, the idea is also to think about what is more in it, right? Replication is data security. It's of course something we know. It gives us reliability and dependability. But from a certain perspective, it is also perfect performance for certain elements. And for what elements I'm talking about, think about the data reads. So it would be bad if you write a lot in this data and we have to replicate it again and again, right? So these data, like Facebook with all their different, let's say, data and so on, or the big data problems often have the character that you read a lot from data. Think about machine learning, right? It doesn't write to data necessarily very much. It reads a lot of data for all the iterations, for optimization, maybe stores the end result or a neural network to the disk. But when it's really about more read-intensive jobs, these frameworks are just beautiful for it. Of course, now you come to the counter part of it and say one negative part of it. If you have a very write-intensive application, then of course you have to redo the replicas. You basically have a problem there. And this is something what, of course, is, however, seen in many companies that they often have a really read-oriented way of working, and this is often happening. So yeah, and the dealing with failure and easy management, we have already said here, mostly also because you abstract again from this layer that you can basically use HBase on top of HDFS, which is very nice. Think about now that you can have many, many different technologies on top of HDFS, which of course are all directly interconnected and can work to each other. And in a way, that's also what we indirectly used in one of our lectures before. You remember we had this idea of saying that basically Apache Hadoop was slower than Apache Spark. Of course, we use here HDFS read just once, and they did HDFS read and HDFS write, HDFS read, HDFS write. And that's how the performance were, of course, slowly dropping because we're really using the file system all the time, right? And here was the idea with Apache Spark, with reading in memory, basically always with the RAM being much, much more quicker than, of course, using the file system. Hence, however, when it comes to really dropping something to file, you see that even, or basically reading from file, even Apache Spark has to use it, right? Because the memory give is basically something where you lose your data. So in this sense, we have revealed a little bit now the counterpart that we had in one of our earlier lectures in lecture 3, where we talked about how that really works with Apache Hadoop. So it uses this kind of underneath, and the kind of version in production really, like HD Insight, like, basically Amazon Web Services, like MS Azure, you always basically have this something where you essentially have always solutions which are optimized for each other. You saw this in the video. The configuration of all this ecosystem, HBase, together with MapReduce in a very certain version in Hadoop, together with Spark, together with HCatalog, together with Zookeeper. This maintenance of creating that yourself is extremely complex, right? So hence, for startups that have their own cluster board and want to install now all of that, it's quite cumbersome, right? And very hard to do. That's why, of course, there is an alternative of using the production systems that you have. In Amazon Web Services was the example of the video with Elastic MapReduce. There you even can scale up, can scale down. You have this Dynamo, you have Redshift, you have many different Amazon services, which are actually very nice connected to this. So it's really tempting to use it on the one hand, but of course, on the other, think about that it's also very much costly if you operate this a long time. So you always have to have the trade-off. If you have customers getting your solutions, you get the return of investment. By no means doing the Amazon infrastructure like Gradescope is doing, right? That helps. But when you're a startup, you have to be also, doing your baby steps, and doing this basically over a long time can also mean bankruptcy because you just keep so many services running. And you see here already the ecosystem on it. So you have something for streaming data analysis, for business analytics, so more statistics, summary statistics, and so on. So data warehousing, database solutions. So this is something where Amazon has lots of services, up to 300 or so. And let's say 100 of them are really nicely connected together to be used with Amazon EMR, because this is a computing, the Elastic MapReduce, where it works. So we have many different services in this ecosystem. And the beauty is it is really together aligned with each other. And here's a kind of sort of smaller overview just for the key essence of functionality that you normally need, right? We need basically this file system. That's what we said. But we had also said that actually we need some data streams to work with it. Or if we have, let's say, relational data sets, right? We can use maybe Scoop. Or we have this computing that we want to know now. We have a MapReduce with Hadoop. So these are all applications in the open source domain that you get with one click in HD Insight, in Google Cloud, in this Cloud Proc that I put you in the resources section, or basically as we have seen with Elastic MapReduce. It's not only MapReduce, which is the point here. The point comes because the ecosystem is so rich. You put lots of things alike. We have this NoSQL data stores with HBase, very powerful. You have seen Facebook using it. Apache scripts with PIC, basically doing much more automatism. SQL is still a big player, of course, when you want to do databases today. And then Mahout is a machine learning library, admittedly a bit older. People would now go to Spark MLlib usually. And with this, having perhaps a more lively community right now, but it still works together with, the whole stack. And when you sharply look in HD Insight here and there on the documentation, you will always find these Hadoop, Spark, HBase, Hive, and all of these different elements, right? Which is there and basically used. So essentially then we have the big data analytics with Hadoop, and the idea with the OpenStack combined in this representation. That is something what we will really learn. Lecture 13 gives us an idea. Now we have to switch the viewpoint. We would say, okay, we don't trust Amazon, we don't trust MS Azure. What we want is actually our own cloud, but we want our own MapReduce cluster, right? So in this sense, you would say that, of course, this is important to then have the basic blocks for that right. So in other words, you can have an OpenStack, everything already pre-prepared for a Hadoop cluster. So there in this OpenStack, that we will learn more about it, people have already done for you the name nodes, the node managers, and the worker nodes. You just have to basically, as Lego pieces, put it to your hardware. So this is the other perspective, right? This OpenStack is a basically cloud operating system, how you can create your own Amazon, so to speak, or your own MS Azure, if you have the resources. And there are different building blocks. Actually, you can have there. Nova is one, which is more the computing part of it. The NameNode then that we have in Hadoop, we need a Nova and a Cinder storage to do this tracking. So you basically can very nicely create it your own if you want, right? It falls back to our discussion last time with hybrid clouds, essentially. And this brings us basically one of the last parts, the configuration and deployment tools with Docker and so on. Of course, there it plays a very big role these days of basically automate it at all. But this is something what we will learn in lecture 12, just to give you an indicator that, of course, we will go back to these interesting tools. We need more material really to cover Docker, containerization, and so on. And finally, some limits, right? You have seen iterative MapReduce can be very costly. You always dump it to file and then do an iterative analysis. So this could be something where there's some extensions right now. When you have seen writes, everything with writing data is really, let's say, not so good. We talked about this PDE solver, so weather forecasts and so on, things in high performance computing and codes, which really need a lot of interaction between in every little time step, right? Simulating the fire in the room here. There we cannot use MapReduce. We use high performance computing to do it. So it's not a solution for everything. That's what I'm telling you about, right? So that is very important. And I think with this, I covered the most aspects. Good, there's a third course hour though. I play, however, the video for the YouTube. It gives you an overview over this, let's say, big data ecosystem a little bit, and the summary essentially of this Hadoop distributed file system. And then we break and have basically a discussion about this assignment 1, if you like.
We all use smartphones, but have you ever wondered how much data it generates in the form of texts, phone calls, emails, photos, videos, searches, and music? Approximately 40 exabytes of data gets generated every month by a single smartphone user. Now, imagine this number multiplied by 5 billion smartphone users. That's a lot for our mind to even process, isn't it? In fact, this amount of data is quite a lot for traditional computing systems to handle. And this massive amount of data is what we term as big data. Let's have a look at the data generated per minute on the internet. 2.1 million snaps are shared on Snapchat. 3.8 million search queries are made on Google. 1 million people log on to Facebook. 4.5 million videos are watched on YouTube. 188 million emails are sent. That's a lot of data. So, how do you classify any data as big data? This is possible with the concept of 5 V's: volume, velocity, variety, veracity, and value. Let us understand this with an example from the healthcare industry. Hospitals and clinics across the world generate massive volumes of data. 2,314 exabytes of data are collected annually in the form of patient records and test results. All this data is generated at a very high speed, which attributes to the velocity of big data. Variety refers to the various data types, such as structured, semi-structured, and unstructured data. Examples include Excel records, log files, and X-ray images. Accuracy and trustworthiness of the generated data is termed as veracity. Analyzing all this data will benefit the medical sector by enabling faster disease detection, better treatment, and reduced cost. This is known as the value of big data. But how do we store and process this big data? To do this job, we have various frameworks such as Cassandra, Hadoop, and Spark. Let us take Hadoop as an example and see how Hadoop stores and processes big data. Hadoop uses a distributed file system known as Hadoop Distributed File System to store big data. If you have a huge file, your file will be broken down into smaller chunks and stored in various machines. Not only that, when you break the file, you also make copies of it, which goes into different nodes. This way, you store your big data in a distributed way and make sure that even if one machine fails, your data is safe on another. MapReduce technique is used to process big data. A lengthy task A is broken into smaller tasks, B, C, and D. Now, instead of one machine, 3 machines take up each task and complete it in a parallel fashion and assemble the results at the end. Thanks to this, the processing becomes easy and fast. This is known as parallel processing. Now that we have stored and processed our big data, we can analyze this data for numerous applications. In games like Halo 3 and Call of Duty, designers analyze user data to understand at which stage most of the users pause, restart, or quit playing. This insight can help them rework on the storyline of the game and improve the user experience, which in turn reduces the customer churn rate. Similarly, big data also helped with disaster management during Hurricane Sandy in 2012. It was used to gain a better understanding of the storm's effect on the east coast of the US, and necessary measures were taken. It could predict the hurricane's landfall 5 days in advance, which wasn't possible earlier. These are some of the clear indications of how valuable big data can be once it is accurately processed and analyzed. So, here's a question for you. Which of the following statements is not correct about Hadoop Distributed File System, HDFS? A. HDFS is the storage layer of Hadoop. B. Data gets stored in a distributed manner in HDFS. C. HDFS performs parallel processing of data. D. Smaller chunks of data are stored on multiple data nodes in HDFS. Give it a thought and leave your answers in the comment section below. 3 lucky winners will receive Amazon gift vouchers. Now that you have learned what big data is, What do you think will be the most significant impact of big data in the future? Let us know in the comments below. If you enjoyed this video, it would only take a few seconds to like and share it. Also to subscribe to our channel if you haven't.
Okay. Yeah, that's all for basically the second part of the lecture. We have the third course hours coming, and basically we'll continue now with the practical lecture 5.1 then on Tuesday. Thank you very much.